Hello everyone, welcome to ML with AP. Today is Sunday and as promised I am back with 5 questions related to data science interview. These are very fundamental questions of statistics which may be asked to you in any of the interviews. Let's get on with the first question. So the first question is explain z-score and also describe how it is useful in statistics and machine learning. Now friends, most of you must be aware about z-score or z-score as we call it. What it is a standard score, and what it measures, it's a numerical value. What it measures the how many standard deviation an observation is from the mean of the distribution. So suppose you have a bunch of numbers, okay, and I give you one other number which is an observation, which is the next observation. Suppose you have n number, I am giving you one more number which is not in the sample, and I'm asking you, hey, what is the z-scores for that? How you will calculate this particular observation, how far it is from, how many standard deviation or how far it is from the mean of the distribution, mean of the original sample. That number is nothing but z-score or z-score as we call it. What is the formula for z-score? The formula for z-score is your z or z as we call it, x minus mu by sigma, where x is our observation, mu is nothing but the population mean, sigma is the population standard deviation. If it is if you are dealing with sample, you have to replace mu with x bar, which is the sample mean, and sigma with s, which is the sample standard deviation. Now let's see that with a clear example. Okay, for that we'll go to this sheet. Okay, to make things simpler, what we'll do is we'll try to now standard deviation and population mean and z-score is valid for any distribution, but to make matters simpler, what we'll do is we'll try to learn it from a Gaussian distribution or normal distribution or bell curve, what we call it. Okay, suppose this is a normal distribution. Okay, this is my mu over here. Okay, and let's say this is my standard deviation, one standard deviation on the positive and negative side. Again friends, this is just to make the idea concrete and simplified. That's why I'm using normal Gaussian distribution. It is not necessary that you have to use it. The same concept will be relevant in other distributions also. Now this is my one standard deviation towards the left and towards the right. Now suppose I have got another, now a new observation x over here. Okay, now a new observation x, and I have to calculate the z-score for this new observation. That what is the z-score? How friends will calculate? We know the mu, we know the sigma, right? What we'll do is we'll do x minus mu by sigma, and whatever number comes, that becomes my z-score or z-score. Okay, this is my z-score. What it is representing? If you look closely, then my numerator, this portion is telling how far it is from my mean, right? X minus mu. What is the difference tell? Difference is telling this difference, right? X minus mu is nothing but this distance. It is telling that how far in actual scale, how far I am, how far is this observation. Dividing by sigma, what it is doing is it is just standardizing it in a scale that, okay, how many standard deviation it is away, because this is one standard deviation, this may be another 1.5 standard deviation. So overall this x point or the new observation is 1.5 standard deviation away. That's what z-score means. Correct? I hope you guys understood this concept. Okay, let's go back. Now the next part of the question was that how it is useful in statistics and machine learning, right? Let's first understand this, that the z-score can be negative and positive also, right? If it is a standard deviation towards the left, 2 standard or 3 standard deviation towards the left, it can be considered as a negative, right? Because the data in the observation can be either on the left of the mean or the right of the mean, or the left of the mu or right of the mu, right? Now where it is used is the next question, right? For that, let's see this particular graph. So one standard empirical formula is 68, 95, 99.7 rule, right? And this is true for normal Gaussian distribution. What it is telling you is that if your mean is this, then this is the probability density function, okay? The area under the curve will represent the amount of data or the probability of the data for that particular range, right? So let's say if I have to say this mu is my mean, right? And since this is a normal Gaussian distribution, it will be symmetric on both the sides, right? Now, it is saying that 68.27% of data will lie in this pink area or whatever color that is. What is that? That means that it is one standard deviation towards the left and one standard deviation towards the right. 68.27% of my data will reside. If you go 2 standard deviation towards the left and 2 standard deviation towards the right, you will capture 95.45% of the data. If you go 3 standard deviation and 3 standard deviation on the right, you will be able to trap or capture 99.73% of the data. So this is the empirical rule, 68, 99, 99.7% rule. So anything beyond this, beyond 3 sigma or beyond 3 sigma on the right or the left, the data, the probability of that happening is only from 0.3%, right? 0.3% is what? Like in a, if you have to see that in 1,000, it will be 3 numbers, right? That's what it is mean. So it's very, very less likely. Anything to occur beyond 3 sigma on the left or right is very, very unlikely. That's why this particular Z score or Z score can also be used in the outlier detection in statistics, right? Because it is giving you that how far the data is from the mean. The farther away from the mean, that means the chances are less and less likely that it is coming from the same probability density, right? Or it belongs to the same distribution, right? That's why the Z score is also used for outlier detection. Friends, I hope this is clear, right? That how this is used for outlier detection. The next is normalization. Now, friends, you must be knowing that in many machine learning models, we have to standardize on what we call normalize the data, so that if my features are on different scales, then my model performance can be impacted. In that particular case, what we do is we try to bring all the features on the similar scale. And one of the ways in which we do normalization is through this thing, making our mean center to 0 and a standard deviation as 1. How do we do that? What we do is that x minus, exactly this formula, what we apply. So here x is all the observation. If we have to standardize or normalize our data set, we have to calculate mu and we'll calculate sigma of data set, right? What we'll do is we'll subtract sigma and divide by a standard deviation for all the numbers. Whatever that new feature is coming or x dash is coming over here, that will become my standardized or normalized data set, right? What is happening over here? If I do x minus mu, what I'm doing? I'm centering mean to 0. And since I'm dividing by sigma, I'm making it a standard normal distribution. What is the definition of a standard normal distribution? Mean should be 0, standard deviation should be 1. So normalization is doing nothing but making a distribution, a Gaussian distribution, to a standard normal distribution. Okay? Okay, so that is another use case of this. The third place where Z-score is heavily used, if you know, is in our hypothesis testing. Okay, let's try to see that with an example. Suppose I tell you that there are 2 exams. Okay, maybe the exam 1, I will tell you that for exam 1, the mean of the number scored by the class is 85 and the sigma is 2, and the average score, which or not the average score, let's repeat this. So mu is 85. The mean score of the students on exam 1 is 85. A standard deviation we know 2. Somebody, a particular student has scored 86 marks. Okay, that is the first. In the second exam, for the same set of students, for the same class, the mu was 85, the mean was 85, the same mean, right? Standard deviation is 10 and he has scored 19 marks. If I have to ask you on which exam this particular person or student did better, what will be your answer? What will be your answer? Think, pause this video and you can think, right? So let's see over here. So my mu is 85 for first exam, sigma is 2, and my score is 87. Okay, for the second exam, my mu is again 85, sigma is 10, and person he has scored 90 marks, right? In which exam he did better? If this is the question, right? What will be your answer? Think carefully. So what we do is we use z-score or standardization or normalization technique over here. We bring both these data set onto the same level playing field. How we do? Our score is 87. We will divide it by mu, which is 85, and we'll divide it by a standard deviation. What is it? The answer is 1. 2 by 2, 1. So my score, what does this mean? This means that 87 is one standard deviation away from mean, right? This is Z1 or Z1, right? In the second score, what it will be? It is 90 is the score, right? 85 is the mean and 10 is the standard deviation, right? What it will be? 5 by 10 is equal to 0.5. Correct? This is 0.5 over here. Now what does it mean? This means that 90 is 0.5 standard deviation away from mean. Okay? Now hold in. Let me draw the figure and it will become clear. This is the mean. This is 85, right? In both the cases. Here my Z1 is what? 1 standard deviation. My Z2 is what? 0.5 standard deviation, right? In which exam he did better? The further towards the right he did, he would do better because he is far away. Somebody would have scored 100 by 100 who would be lying over here, right? Further towards the right he scores, he will be better. In the exam 1 he has scored actually 1 standard deviation away towards the right. In exam 2 he has scored 0.5 standard deviation only away. So even though he has scored 90 marks in exam 2 and only 87 marks in exam 1, he did better in exam 1. Z1 score is 1, Z2 is 0.5, so he did better in Z1 exam, right? It is not very intuitive, right? You will see that, oh, okay, both the means are same. Both the means are same, and here he has scored more marks. So let's call Z2 as that he has done better in the second exam. No, he has done better in the first exam because he is away 1 standard deviation. In exam 2 he is only away 0.5 standard deviation. Okay, so that is another place where it is used. Okay. Yeah. The another place, this is on the standardization side only, right? The other place where it is used is over here, right? For the hypothesis testing. Okay. Now let's take another example for the, I do not want to deal the entire hypothesis testing. If you have to, please, probably, if you know a bit about hypothesis testing, maybe I will try to explain where z-score is used, right? Now, this is a normal Gaussian distribution again. Let's say, suppose somebody asks you the question. The question is that, let's frame the question. So, the question is something like, okay, in a class, so there was a test, right? Let's see, there is a test which is conducted all over India, right? Some entrance exam test or something. And the mu is, the population mu, right, is, let's say, it's a 100-mark question and 100-mark paper, and the mean is like, let's say, 65, okay? This is, so in hypothesis test, if you know, we always say somebody come and claim that no, the mean is not equal to 65. The mean is not equal to 65. This is somebody is claiming. Now what we do in hypothesis testing, we always have a null hypothesis, right, represented by H0, and null hypothesis is always a status quo. So we'll see that, let's see, null hypothesis is always our status quo. So we'll see that 65. Alternate hypothesis is that mu is not equal to 65. Somebody is claiming that not equal to 65, and he is saying that. So what we have to calculate? We have to either reject or fail to reject our null hypothesis with what? Confidence interval 95%, or alpha A becomes 0.05. It will be 1 minus 0.05, 1 minus 0.95, that will be alpha. So both confidence interval and alpha is saying the same thing, right? Now this is the question in the hypothesis testing, and friends, I hope you have a brief background because I am going a little fast over here. Okay, what we'll do, how we'll solve this? What we'll do over here is, again, in a normal distribution curve, right? What we'll write? Will it be a two-tail test or one-tail test? It will be a two-tail test, right? So we'll say that alpha is 0.05, right? So 0.025. This is the area, right? And on this side 0.025. This is the area, my rejection area, right? This is my rejection area. This is 65, which is the mu. Okay, over here in this particular area I will be fail to reject my null hypothesis, correct? And over here towards the right, the shaded area, if my claim lies towards the shaded area, I'll be able to say that I reject the null hypothesis. Okay, and there is a strong evidence that my mu is not equal to 65, right? Correct. This is how hypothesis works. Now I do not want to go into proving or not proving the hypothesis, because we do not have the standard deviation and number of samples and all those things, right? But the way it is calculated, you can calculate is that you should have standard deviation, you should have the observations, right? And then what you will do is you will try to calculate the z-score, right? The z-score. And what the z-score will come? The z-score will nothing but your h minus mu by sigma by root n, right? In this particular case, a standard error. And the whole point I'm trying to make is, suppose your z-score lies over here, these many standard deviations, right? And it lies in the region, which is covered, which is rejection region, right? In that particular case, you can reject the null hypothesis, and you can say that there is a strong evidence that my mu is not equal to 65, right? If my z or z lies in fail to reject region, this particular region, then you can say that I do not have enough evidence to either accept or reject the null hypothesis. So I do not know whether the mu is 65 or mu is less or greater than 65. I do not know, right? So that's the basis. So z-score is also used in hypothesis testing, right? Correct? Okay. With that being said, I think we probably covered in enough detail that what is z-score and how it is useful in statistics and machine learning. I will close this video again, and let's see you in the next question.